Hi everyone, so welcome back, welcome to lecture 8. So we will now proceed towards again developing more of this language of G's, F's and so the free energies, right. So the for closed systems and open systems, the potentials of relevance for us, okay. So in the last class we have seen a bit about vacuum systems and so how G is the relevant free energy functional for us. So we take that as something that where we can do material synthesis, where we can control temperatures and pressures, and G becomes the obvious choice for implementing second law of thermodynamics. Okay. All right. So let us begin this class by actually recounting all the potentials that we have seen and not seen, right. So for example, we started with the first law of thermodynamics. Let me use a different color. Let me use red. We started by looking at the first law of thermodynamics. Let us write everything in the differential forms. Let me redo this. Let us write all the potentials in differential form. All the thermodynamic potentials that we studied so far, right. So the first thing is du, and du we know is TdS minus PdV, right. Now from the sort of understanding we have gained so far, we can say that the relevant thermodynamic potential, if I have control over the entropy. Now that is a difficult thing to do, right. If I have control, if I can change entropy at my will, and if I can change the volume of the system at my will, the relevant thermodynamic potential then will become du, right. It is not dF or dG, it will become du, right. So this is what the so if I rephrase the first law of thermodynamics in this fashion, right. So the relevant thermodynamic potential for me, that is why energy minimization comes from this, right. So where I have control over entropy and where I have control over the volume of the system, right. So then I can minimize the internal energy of the system, right. However, that is so getting a control on entropy is not always so straightforward. But what we can get is a control over temperature, and when we get control over temperature, I have a minus SdT minus VdP, right. So here that is Gibbs free energy, but minus PdV. So here I have a control over temperature and volume, here I have control over entropy and volume, right. Then dG, where I have control over temperature and pressure, the most important free energy is so minus SdT again, right. So wherever temperature control comes, I get a minus SdT, right. So plus a VdP, okay. Something else we missed, right. So SV, TV, TP. So what about S and P, where I have control over temperature, entropy of the system. Now how, where, in what processes do I have control over entropy? We are going to look at it very soon, right. Now this is again TdS, since I have control over entropy, and plus VdP. In fact, this is a quantity that I am going to write as H, right. H I am going to write it as E plus PV, just like I have written F as or U plus PV, right. Just like I have written F as U minus Ts, G as U minus Ts plus PV, right. H, right. So this is how I have defined all these free energy functionals earlier. H I am going to write as U plus PV, and so if I take a dH is equal to du plus PdV plus VdP, and that will give me TdS plus VdP, right. So du is nothing but TdS minus VdP. So VdP gets cancelled and I have TdS plus VdP, right. So this H, the way you define this H is called the enthalpy of the system. It's derived from free energy, it's derived from internal energy, but the point is, if I have control over the pressure that I can so if I am doing constant pressure processes, or if I have control over pressure, right, and control over entropy, then the relevant thermodynamic potential for me is the enthalpy, right. So, it is not free energy, it is not Gibbs free energy, it is the enthalpy of the system. Okay. So, this is called the enthalpy or differential change in the enthalpy of the system. All right. Okay. Now, let us in the next page let us again rewrite all these things, this time a bit you know. So, du equal to T ds minus P dV, dH equal to T ds plus V dP, dG equal to dF is equal to minus S dt minus P dV and dG. So, this is F. What is this? Minus S dt plus V dP. Okay. These are the 4 functionals, thermodynamic functionals I defined for what are called closed systems, right. We are going to modify them for open systems, right. So, we are going to build up and then modify, so if mass is being exchanged between system and surrounding, how do these potentials change. Okay. So, that we are going to do in the next class, but all right. So, then so let me take a functional like df, right. So, let me take this and then do some operations, right. So, if I am looking at how is really so this is all telling me how to go from one f to another f, right. So, how do I change the free energy functional, the Helmholtz free energy of a system, right. At a given equilibrium condition, I have control, or it is at a constant temperature and constant pressure, and then by changing the internal constraints it is coming to an f that defines the equilibrium of the system, an f minimum that defines the equilibrium of the system. But when I change these constraints, then it goes to a new f minimum, a new equilibrium, right. So, how does one f minimum, one equilibrium f go to another equilibrium f, and that is given by so this relationship, okay, this differential relationship. Okay. Now, then it is straightforward to ask the question, all right, that is fine, but then if I change temperature by 1 degree, how much is my free energy functional going to change? So, essentially I am asking this question, if I change if I change dt by 1 degree, how much is df going to change, and that comes, and I do not want to change anything else, I want to keep the volume constant, because f is also independently dependent on the volume, right. By changing temperature, if volume itself is changing, then so it becomes difficult for me to understand this. So, I am going to ask, what is this differential mean, right. So, how much do I change the f by changing temperature by 1 degree, and that is nothing but minus S, right. So, it just depends on the entropy of the system. Entropy is something that is well defined, right. So, entropy we will look at third law very soon, but entropy is defined with precise values. It is the number of microstates of the system that I can count and then get to the entropy of the system, K, L and W, right. So, entropy is well defined. So, based on entropy I can say what is dou f by dou t. Dou f by if in a gaseous system where the entropy is larger, dou f by dou t is larger, right. So, f will so just by changing temperature by 1 degree in a gaseous system, f will reduce much more steeply, right. In a solid system, however, entropy is smaller, right. So, that is how we imagine, right. So, and if entropy is smaller, then dou f by dou t is also small. So, f will change with temperature, will decrease with temperature, but in a very with a little slope, right. So, we will plot all these things and try to see. However, let me also do this operation, dou by dou t of dou by dou So, dou by dou v of dou f by dou t. Now, that is some minus dou s by dou v, right, and minus dou s by dou v turns out to be some kind of a material property, right. And this material property, you can call it some gamma or something like that, where by changing the volume of the system, how do I change the entropy of the system, okay. So, of course, by changing the volume, entropy should change, right. So, entropy is an extensive quantity, and changing the volume of the system should change the entropy of the system, but how much do I change it by, and this equation tells me how much I can change it by, right. Yeah, okay. So this is a material property, right. So it's some kind of a material property that tells me how much I can change the volume of the system. By changing volume of the system by, let us say, a little bit dV, how much is the additional entropy I am putting in the system. I am putting in additional states into the system. How many states am I putting into the system? That changes from solid to liquid to gas, that changes from material to material. So this is a material property. Okay. So here I have a material property that is defined, but you can see that it is defined as a second differential of the free energy. Okay. Now f is what is called an analytical function, right. Now whether I do, which means essentially here I am doing dou 2 f by dou v dou t, right, and that is equal to, first here I did a differential with respect to temperature and then I did a differential with respect to volume. I can change the order of differentiation, right. So I am going to first differentiate with respect to the volume keeping temperature constant, and then I am going to take a differential with respect to temperature. Okay. Now if I take a differential with respect to the volume, what am I getting? I am getting a pressure, right. So minus dou p, right, by dou t, and this is all done at a constant volume, right. So at that temperature and volume, this depends on temperature and volume eventually. Okay. All right. Now since f is an analytical function, these two are equal, or in other words, you know, how I change the pressure of the system by changing the temperature is exactly the same as how I change the entropy of the system changing the volume, right. Now this is also another property of a material, right. So how much am I pressurizing the material, how much am I stressing the material by applying temperature, right. So this, let us call this some kind of you know, so I change temperature and the material is stressing even more, right. So this is some property of the material. Let us call this the stress temperature coefficient of stress or something like that, right. How much am I stressing the material by applying temperature, right. So effectively you can think of a railway track or something like that which is clamped, right. So I increase the temperature, I am, you know, so I am constraining this, right. So from expanding, so as a result, you know, so it is, I am building up some kind of a stress or pressure, right. So by constraining it to expand, I am building up pressure, and how much pressure am I building up by changing the temperature, that is what gives me dou p by dou t. Okay. So what this equation essentially is saying is there are two seemingly unrelated properties, one is dou s by dou v, that is exactly equal to dou p by dou t, right. These are two seemingly unrelated properties. Okay. So how much I increase the entropy by changing the volume is the same as how much I increase the pressure by changing the temperature of the system, right. I mean, these are two different experiments altogether, right. So how do I change the pressure of the system by increasing temperature? I have to have a pressure gauge, I then increase the temperature and then see how I am changing the pressure of the system, right. But you know, so apparently I do not need to do that experiment. Instead I can do an experiment where I change the volume and then measure the number of states, number of extra states that this system can take. Okay. Now measuring entropy is another thing, right. So it is not a straightforward thing. However, having said that, you know, these two material properties look independent, but they are related by the fact that f, the free energy functional that I take, is an analytical function. Okay. Now, similar exercise you can do with G. Now, dG is given as, I think I will use this color, right, so that it is more legible to you. dG is given as is it minus VdP minus SdT, right. So, I can do the same thing, dou G by dou P, dou by dou T, right, is equal to, how much is this? This is dou V by dou T, and I know what dou V by dou T is. This quantity I exactly know what it is, because it is the change in volume by changing the temperature, and this is coefficient of thermal expansion, or the volume coefficient of thermal expansion, right. How much is the volume changing by changing the temperature in an unclamped scenario. Okay. Now, that is equal to dou by dou P, dou G by dou T, right, and that is equal to minus dou G by dou T is minus dou S by dou P, right. Now, I am changing the pressure and looking at the change in the number of states of my sample, right. So, if I apply pressure, how is the entropy changing, right. Now, you can call it some kind of this is what is called a piezo-caloric effect, which is I am generating entropy, or I am generating some heat by applying pressure. Okay. Now, apparently this actually tells me that negative of piezo-caloric effect is the same as volume coefficient of thermal expansion. And all this happens because G is an analytical function. This is just a mathematical consequence of my properties being equal, right. Right. So, I mean, there is a huge body of work that comes out of these sort of relations, right. So, these are what are called Maxwell's relations. That ideally they relate properties that are seemingly different properties, right. So, but they get related because of thermodynamics, right. So, in context of understanding properties from thermodynamics, this becomes important, and this is so part of the other course that I give, that is what is called principles of materials design. And this is already an NPTEL course that you can go and look at the second module in this course, where I again do thermodynamics, but with relation to understanding the properties of materials coming from thermodynamics and StatMech. Okay. So, so this is just an advertisement, but so you see that just by defining these thermodynamic functionals, the second differentials of these thermodynamic functionals happen to be properties of materials, and these properties so are seemingly independent properties get related. Right. So, just like we took the example of F, we took the example of G, and we say that seemingly independent properties get related. Okay. So, all right, now you can do the same thing with du. Okay. So, TdS minus PdV, here also so dou U by dou S, dou by dou V is equal to dou U by dou V, dou by dou S, and minus comes, and that means dou U by dou S is dou T by dou V, right. I mean, somehow you are changing the temperature by changing the volume of the system, everything is related. I mean, there is a state of equation that relates everything to everything, right, and that is exactly the same as changing the pressure by changing the entropy of the system, or negative of that, right. So, I mean, this is actually the inverse of the previous equation that we have seen, and so you can, for completeness, you can also say dH is TdS plus VdP, right, and so dou H by dou S, dou by dou P is equal to dou H by dou P, dou by dou s, and that tells me that dou h by dou s is T, dou T by dou P, again change in temperature with pressure, another state variable, is equal to change in the volume, right, with the entropy of the system. Okay. So, so these are what are called, these are the 4 Maxwell's relations, Maxwell relation, relation, this is also a Maxwell relation. Okay. So, again just I can just do this for several different functionals, right. So, I can define other thermodynamic potentials also, which I do in the other course, but so Maxwell's relations actually relate independent properties of materials, and these properties of materials so tend to be the second derivatives of my thermodynamic free energies or thermodynamic potentials. Okay. Okay. Now, with that slight digression, because so this is also important for you to just realize the extent of thermodynamics, that so I can look at, it's not just functionals are not just for understanding processes, but it's also important to understand properties of materials, right. So, thermodynamics has everything in it. It tells me how to design a process, a material synthesis process, but it also tells me how to understand a property of the material, right. That so thermodynamics is in that way very rich, right. So, these functionals, these potentials that I am defining is quite rich. Okay. Okay. So, with that, let us define what is called a standard state. Let us just change the gears a bit and look at some real world examples, right. Now, what is a standard state? Standard state is the most stable phase or structure of a material at 1 atmosphere. Okay. So, this is what I am going to define as a standard state. Then if I tell you that standard state is standard enthalpy, right. So, I am going to define a standard enthalpy as H naught of T. Now, H naught of T means this is the enthalpy of the material at a temperature T, but pressure 1 atmosphere. Okay. So, that H naught comes here, H naught means 1 atmosphere. I am not going to say that this is equal to H of T comma 1 atmosphere. Okay. Then entropy, right. So, of standard entropy means entropy at a temperature T and 1 atmosphere. Okay. Similarly, so I can define a free energy G naught of T, right. So, G naught of T means G at T / 1 atmosphere. Okay. So, this is what is called a standard state. So, and in this case we call this the standard enthalpy. In this case we call it standard entropy, or let me change the color so that it is easy for you to look at it. This is the standard. Okay. This is the standard entropy, this is what is called the standard free energy. Okay. Now, let us solve some problems in this class, right. So, using these standard states, because this is what becomes relevant again. Now, I ask you the question, how does H naught of T vary with temperature, right. So, this is all at one pressure, right. So, how does H naught of T vary with temperature? Let us take the simple example of water, ice to water to vapor, right. So, transition. Okay. Now, so so H naught of so this has some phase transitions, and the phase transition occurs at let us say 0 degrees Celsius, it also occurs at 100 degrees Celsius, right. So, below 0 degrees Celsius, this is all in the so this is the ice phase. At 0 degrees Celsius there is going to be a discontinuity, okay, and so of H naught T, and this is going to be in water. Let me just draw it with a different slope. this is going to be liquid, right, and at 100 degrees C there is going to be even more another discontinuity, and this is going to be gas, right. So, this we have seen or this you may have recognized from your earlier classes, that enthalpy of a phase increases with the temperature A, and B, the sudden jumps, there are sudden jumps wherever there are phase transitions. Enthalpy or the standard enthalpy jumps at phase transitions. Okay. Now, what is the slope dou H naught by dou T, dou H naught T by dou T, right. So, we see that the slope is somehow larger in the ice phase a bit, I mean the way I have drawn it, right. So, it is a bit smaller here in the liquid phase, and in the gas phase it is almost flat, right. So, that is how I have drawn it, right. What is this? This is nothing but, again, it is the property of the material. It tells me how much, so I change the temperature by 1 degree, how much heat, how much enthalpy I am putting into the system, right. Now, by now enthalpy, we have all these definitions of enthalpy. I am doing it at a controllable pressure, controllable temperature. So, the only form of heat I can give to the material is enthalpy, a quasi static heat I can give to the material is enthalpy, right. So, under constant pressure, that means, right, or in this case the pressure is 1 atmosphere because H naught is a constant. By changing the temperature by 1 degree, how much heat am I putting into the system, okay, and that is given by Cp, or it is the heat capacity. If I do this at constant volume, then I have dou U by dou T at constant volume, that is Cv, right, but this is Cp, okay. So, just for comparison, this is also a material property. So, the way you count Cp is by counting the number of degrees of freedom, right, and you see that for solids Cp is larger than liquids, where Cp is larger than gas phase, okay, or Cv, it does not matter, okay. And that is because solids have a lot of ways in which they can get heat, or so distribute heat among themselves, right. So they are vibrating, right. So they have several degrees of freedom, right. So they have their kinetic energy, but they have their vibrational energies, right. So they have about 6 degrees, every molecule has about 6 degrees of freedom, right, 3 potential, 3 kinetic. Whereas gases have only, so they can only move, right. So they have only 3 degrees of freedom. So the solids have a larger Cp than gases. It becomes 3 kT here and 3 by 2 kT there, right. So 3 kT to 3 by 2 kT in a very simple simplistic high energy approximation, okay. And so that determines these slopes, right. So solids can get heated up more easily than gases. This we know, right. So if I start heating up, so if I have some heat source and start heating up some metal, of course at the edges I can easily feel that this is more hot than when I start heating up a gas molecule, so just have a lighter here and just light up this, so keep a lighter and then touch here, right. So there is some heat conduction, etc., happening. But so the heat capacity already tells you that the air molecules are not getting as hot, right, in terms of temperature, because I can feel the temperature on my hand than the solid molecules, right. So solid molecules get hotter faster, right. I mean fast and other things are kinetics, again I want to caution you here, but just the heat capacity, how much can I heat, how much does the temperature rise, how much do I heat the material by changing the temperature by 1 degree, right. So that is the heat capacity, and for solids it is much larger than gases, okay. All right. So and liquids are always in between people, right. So they are neither there nor here. So I look at that, I look at this, I take my neutral territory, okay. But the important thing is, at the phase transitions at 0 degrees and at 100 degrees there are these sudden jumps, right. What are these sudden jumps called? This is called latent heat of fusion, right. So the H naught liquid at 0 degrees Celsius minus H naught of solid at 0 degrees Celsius. This is what is called latent heat of fusion. Right. Somehow there is more heat in the liquid, right. So, I do not I do not need to change the temperature at all, but liquid seems to be more vigorous and more energetic than the solid, right. Similarly, this you can easily feel with gases, right. At 100 degrees Celsius, the H naught of gas or water vapor in this sense minus H naught of water, that is called latent heat of it is not fusion, it is vaporization, right. So, this is latent heat of vaporization. In other words, I can touch a molecule at 100 degrees, a water vapor molecule at 100 degrees, and I can touch a liquid at 100 degrees. I feel more pain by the molecule that is coming and hitting me, which is in a gaseous phase at 100 degrees Celsius. That has more energy, right, than the liquid phase. Okay. So, where is that energy coming from? That is some latent heat in thermodynamics, so before I understand all this bonding structure, etc., I am going to say, all right, there is some latent heat that is actually affecting me more than the heat that affects me in the liquid phase, right. So, both of them are at 100 degrees Celsius. However, in one case there is some latent heat, some extra latent heat, right, than in the other case. Okay. So, this is called latent heat of vaporization. So, near phase transitions, I always have discontinuities or sudden jumps because of this latent heat in H naught, because of latent heats, and they show up in phase transitions. Okay. At phase transitions. Right. Okay, fine. Now, let us do the same thing for G naught of T as a function of T. Okay. Now, how does G naught? So, then I have to understand what dou G by dou T is. Dou G by dou T is equal to minus S. Dou G by dou T, keeping the pressure constant, is minus S, right. So, then so again this is 0 degrees Celsius, this is 100 degrees Celsius, right. So, I am going to draw this as so minus S, right. So, S is a positive number, entropy is always a positive number. So, the free energy, the Gibbs free energy will decrease with temperature, the standard Gibbs free energy, this is standard Gibbs free energy. Okay, will decrease with energy. Okay. All right. However, Gibbs free energy has this quantity, there is no latent Gibbs free energy, right. So, Gibbs free energy is always a continuous entity, right. However, so at 0 degrees Celsius, I am moving from a solid phase to a liquid phase. Now, liquid phase has more entropy than solid phase, right. So, liquid is sort of accessing more let us say microstates, right. So, it has a larger free volume. So, you can think of, or more random in some sense. So, you can think of liquid having more entropy than solid phase, right. So, the slope increases, or the negative slope increases in some sense, right. So, that is where it is, and then it vaporizes. So, the slope even more increases, right. But you see that in G is not discontinuous, right. G itself is a continuous function, but at the phase transitions there are these kinks, okay. Or in other words, dou G by dou T is discontinuous. If I plot S naught as a function of T, right. Now, S naught as a function of T, that is a discontinuous function, right. So, that just like H naught, right. So, that increases actually, yeah. So, and then so there is a discontinuity that increases, and again there is a discontinuity, right. So, S naught as a function of T shows discontinuities with a slope again dou S naught by dou T, that is actually Cp by T, right. So, this is solid, this is liquid, this is gas, but G itself does not have discontinuities. The differential of G with respect to T, right. So, though that has discontinuities as at phase transitions. Okay. So, this is something important to understand, right. So, at phase transitions what is happening. Okay. And so dou G by dou T is nothing but minus S. This is not a material property, this is just the entropy of the material, right, whereas Cp is the material property, right. So, material properties, so the S undergoes some discontinuities because the properties are abruptly changing, right, but the entropy is continuously changing, right. So, entropy of the liquid is more than entropy of the solid, and entropy of the gas is much more than entropy of the liquid. Okay. So, that is how your G will evolve as a function of temperature, right. So, these are all equilibrium G's, right. So, I have fixed the pressure, I am just changing the temperature and I am seeing, alright. So, here my equilibrium G is here. What will happen when I increase the temperature to about 20 degrees Celsius? The equilibrium G shifts, right. This gives me the trajectory of equilibrium standard Gibbs free energy. Okay. So, this curves give me the trajectory of standard Gibbs free energy. All right. Okay. So, with that, let me define another convention, right. So, for example, S naught, right, at a given temperature, I can define this to be a unique value. Why? Because I am going to come to the third law of thermodynamics, but third law of thermodynamics tells me that S naught at 0 equal to 0. This is my reference value. Okay. But H naught, I do not have any such similar references coming from laws of thermodynamics, right. So, I am going to just define that H naught at room temperature 298 Kelvin, right, for pure materials or pure materials, right, that is equal to 0, right. So, this is my reference state. If I have reference, I can then say, so I can just give you a number for H naught, and then it is always with respect to this reference state. That is with the definition that for pure materials H naught equal to 0 at reference state. Okay. Now, what is a pure material? Pure element rather, not a material, pure elements, right. So, H naught for at 298 Kelvin for anything in the periodic table, you take hydrogen, helium, manganese, nickel, so I mean I am not writing periodic table in order, as you can already see, copper, barium, titanium, oxygen, so hafnium, gallium, nitrogen, right. So, anything, any pure element, right, it is not, I am not taking gallium nitride, I am just taking either gallium, pure gallium or pure nitrogen, right. H naught at 298 Kelvin, I am going to define that to be 0. This is my reference state. Okay. So, for all these pure elements. Okay. Then you may ask the question, let me take a mineral, right. So, and this mineral is manganese silicate, right, something which is actually called I think this is called rhodomite or something like that. Let me just check. Yes, this is called rhodonite, right. Now, if you look at papers, if you look at theories, they say, oh, you know what, I have what is called the enthalpy of formation of rhodonite, right, which means so this is a standard term that people keep asking, right. So, what is the enthalpy of formation of your compound? Now, I am moving from pure elements to compounds, right. So, what is the enthalpy of formation of MnSiO3? For some reason this is of interest to me. Okay. So, rhodonite, all right. Now, so then the question is, okay, so what does it really mean, enthalpy of formation of rhodonite or MnSiO3? So, I am going to say this rhodonite or delta H of this, okay, this rhodonite MnSiO3 is going to form from pure elements, right. So, this is the reaction that I am going to write, Si plus 3 by 2 O2, right. So, rhodonite has formed from pure elements. And it has formed from pure elements at 0 Kelvin, sorry, at room temperature, let us say 298 Kelvin, right, at 298 Kelvin. Okay. All right. Now, since it has formed from pure elements using this reaction, I am saying the delta H formation of rhodonite is nothing but the delta H is nothing but of the reaction that I wrote here, right, at 298 Kelvin, because these are the pure elements from which the rhodonite is formed. And then H, then I know that so at 298 Kelvin H naught of Mn is equal to 0, H naught of Si is equal to 0, right. So, this is at 298 Kelvin, this is at 298 Kelvin, and I know that H naught of oxygen is equal to 0, right. So, essentially the formation the delta H of formation of this reaction is nothing but the delta H of formation of MnSiO3, or the delta H of this reaction, right. So, delta H of reaction 1 is defined as delta H formation at 298 Kelvin is defined as delta H formation of rhodonite. Okay. So, I can easily define what is the delta H formation of rhodonite, right. So, it is essentially the delta H of this reaction, and this reaction so at 298 Kelvin I have, by referencing, I have defined that this is 0, this is 0, this is 0, and so the delta H formation of so the delta H of this reaction is nothing but the delta H of formation of rhodonite. Okay. Okay, let us keep that in mind. And so, all this comes because so H is not, or H or G, right, these are not absolutely defined. For to define G and H we need absolute references, right. Now, what happens to delta G naught at 298 Kelvin, and delta G naught just becomes H naught at 298 Kelvin plus so H plus Ts, right. So, the G equal to E U plus PV plus Ts, right, and U plus PV is nothing but H, right. So, H plus Ts. So, plus T is 298 Kelvin times S naught at 298 Kelvin, and S naught is something that is defined from third law of thermodynamics. H naught is something that I know, either it is the delta H of the formation, I mean, so of this reaction, right, or it is for a pure element it is 0. So, for a compound I just write the reaction and then estimate the H naught. For a pure element it is 0. Okay. Okay. With this, let us solve some problems, and and by solving these problems we will go into the idea of third law of thermodynamics. Okay. So, so far so we have in this class we have actually very quickly defined so some of the reaction terminologies, right. So, enthalpy, we have defined enthalpy for the first time. We said, all right, so thermodynamics is not just to understand processes, but also there is a so another way of looking at thermodynamics to understand material properties, right. So, we looked at what are these Maxwell's relations, but having so done Maxwell's relations, we then wanted to bring you back to processes, and most of these processes initially involve some chemical reactions. So, to understand the language of chemical reactions, we defined some standard things, right. So, what is standard enthalpy, what is standard entropy, what is standard Gibbs free energy. So, all these standards are defined at 1 atmospheric pressure, assuming that everything is happening at 1 atmospheric pressure. Once you change the pressure, we are not anymore talking about standards, right. And in this 1 atmospheric pressure, so for enthalpy and Gibbs free energy we need to define some referencing. For entropy, third law of thermodynamics takes care of referencing. So, there is some reference entropy that we enthalpy that we have defined for all the elements, which said that H naught at 298 Kelvin is 0 for all pure elements, and based on which we have estimated H naught at 298 Kelvin for all the compounds, right. So, it is just the delta H formation of that reaction. Okay. of that compound from individual elements. Okay, so that these delta H's are estimatable. I think they are also not I think I know that they are measurable, right. So you can measure delta H and then actually give data tables with data of delta H of various different minerals. People have done that over a course of so many years of research, right. So now you can get data sheets with delta H formation of various minerals, various compounds, and so on and so forth. But what does delta H formation mean? It essentially means this. Okay. So now based on this, I think now we are in a stage to understand some chemical reactions. I think this will go back to some physical chemistry that you may have done in your class 1, class 11 and class 12. But so we'll just recap it and then understand this from the perspective of the fact that reactions are important when you are doing synthesis. The first thing that should happen is some kind of a chemical reaction. I want to grow rhodonite, thin films of rhodonite. So first, if I am using source of manganese, silicon and oxygen, I want them to react in a certain way that it gives me rhodonite first, right. So first, the primary most important things are chemical reactions and and phase transitions, right. So everything, all growth is chemical reactions and phase transitions. Okay. The thermodynamics of growth, right. So and then comes the kinetics. Okay. So we'll look at that in the next class. Okay. So we'll try to solve some reactions and then gradually move towards the third law of thermodynamics. Okay. All right. Thank you very much.